Most atoms are stable, very stable. Some have been around for over 13 billion years and will still be here much longer than that into the future. A few, however, suffer from an imbalance between the number of protons and the number of neutrons in their nuclei, and these can spontaneously transform themselves by readjusting that ratio and spitting out the constituents that are unneeded. The timescale on which these unstable nuclei undergo their transformations is immutable. Freezing an atom, locking it in a crystal, bombarding it with light, dumping acid on it, nothing will change that steady rate of decay. As a consequence, these nuclei provide imperturbable clocks to the atomic historian, allowing us to date precisely everything from the mortar used to hold together stones in ancient buildings, to glacial ice laid down over hundreds of thousands of years in Antarctica, from human bones we uncover in excavations, to the meteoric material out of which the solar system was born. Within a decade of the elucidation of the structure of the atom around the turn of the 20th century, strange phenomena were observed. It was only understood then that there was a positive component and a negative component to an atom, and that the positive component was concentrated in the center. Neutrons, for example, had not yet been detected. But it was observed that while most atoms remained placid and unchanging, a few kinds spit out very high-energy particles at random times. The identity of these emissions were at first a mystery, although three different types of particles that came out were differentiated, and they were, because they were unknown, given the first three letters of the Greek alphabet, alpha, beta, and gamma. We retain those names today, despite the fact that we now know what they are. Their identities are as follows. An alpha particle is actually the nucleus of a helium atom, 2 protons and 2 neutrons stuck together. A beta particle is either an electron, a simple electron, or its antimatter counterpart, the positive electron called a positron. And the gamma ray is just a high-energy photon, the extreme end of the electromagnetic spectrum we discussed last time. This process of spontaneous transformation in the nucleus of an atom was given the name radioactive decay, despite the fact it has nothing to do with radios, and it's not really a decay. Radio was then used in the sense of radiant energy, energy just emerging from some process, and decay was because these atoms changed in form. But of course, there's nothing worse about a nitrogen atom, which is the result of the decay of a carbon-14 atom, and so decay is also not an accurate description. Nonetheless, we will stick with those terms because that's the terminology that physicists still use today. At first, only certain heavy elements were implicated, but lighter, unstable species were soon observed. It became clear that only certain isotopes of each substance, of each element, were unstable. A total of about 70 naturally occurring radioactive isotopes are now known to be unstable to alpha or beta decay. Any isotope of any atom, actually, can be stimulated to emit a gamma ray if you perturb it enough, if the nucleus gets excited by some external particle, but some occur naturally and some are produced artificially. Alpha and beta decay realize the dream of the alchemists. They transform one kind of an element into another, not, unfortunately, lead into gold. In alpha decay, the nucleus loses 2 protons and 2 neutrons, and therefore jumps 2 spots down in the periodic table. In beta decay, one of several things can happen. If a neutron inside the nucleus spits out an electron and transforms itself, therefore, into a proton, going from neutral, losing a negative charge, and therefore becoming positive, the element moves one step up in the periodic table because its atomic number, its number of protons, has increased by 1. If a proton in the nucleus spits out an anti-electron, a positively charged thing which turns it from being positive into being neutral, or a neutron, the element therefore moves down 1 step in the periodic table because it's lost a positive charge. If the nucleus manages to capture, gobble up, one of the innermost electrons that's orbiting it, and this can happen on occasion, then it adds a negative charge to the nucleus, transforming a proton to a neutron, and therefore again moving 1 step down in the periodic table. Gamma decay is simply the emission of photons by an excited nucleus, and as such, a gamma decay does not change the identity of the element itself. After alpha or beta decay, the resulting nucleus, having lost some particles all of a sudden, is often left in an excited state, meaning that gamma decay frequently follows and is accompanied by one of these other transforming decays. A nucleus can be excited also by bombarding it either with photons or other particles from outside, and thus be induced to undergo a gamma decay. We'll see an application of that in the next lecture. Now, since these decays are absolutely central to so much of this course, it's worth it to look at them in a little more detail, taking them one at a time. With examples. Alpha decay. This typically occurs for heavy elements, elements high up in the periodic table with large numbers of protons and neutrons. Let me use bismuth as an example. Bismuth is number 83 in the periodic table. It's got 83 protons, and the isotope of interest here is bismuth 212, meaning 83 plus 129, 212 particles in the nucleus. So it has 83 protons and 129 neutrons. That turns out to be an uncomfortable ratio, just a few too many neutrons for the number of protons there, and so bismuth 212 will spontaneously spit out an alpha particle, 2 protons and 2 neutrons, effectively the nucleus of a helium atom, and transform itself into thallium, number 81 in the periodic table, 2 steps down, thallium 208. The alpha particle just zips away, eventually finds a couple of electrons to hook up with, and ends up as a helium atom. It turns out, incidentally, that this is the source of almost all the helium on Earth today. While helium is the second most abundant element in the universe, second only to hydrogen, making up about 25% of all the atoms in the universe, there is virtually none left on the Earth. When the Earth first formed, hydrogen and helium, as with every other planet, were dominant. But because the Earth's gravity is so weak, and because it's relatively close to the sun and therefore warm, the atoms in the atmosphere that are light, traveling fastest, as we've discussed, can escape. And the Earth lost its initial hydrogen and helium atmosphere. Only heavier atoms, like in oxygen and nitrogen and water and carbon dioxide, remain in the atmosphere today. We'll explore this in much more detail when we look into the paleoclimate history of the Earth. However, helium today on Earth comes almost exclusively from radioactive decay. In the crust of the Earth, various kinds of heavy atoms undergo these decay, spitting out helium nuclei, which then acquire electrons and become helium that you can fill your party balloon with. This is typically collected when oil wells or gas wells are drilled, and this gas, which has been trapped deep in the Earth for a long time, emerges. So helium today all comes from radioactive decay. In general, then, we can write this kind of equation, this kind of decay, as the original nucleus, which we call the parent, decaying into the subsequent nucleus we call the daughter, and an alpha particle. We always write the atomic number of the element at the lower left of its symbol, you will recall, and we give it the symbol Z. We write the atomic mass of the number on the upper left of the symbol, as you will recall, and that we give the letter A. And so the equation for any alpha decay looks like a parent of atomic mass A and atomic number Z decaying into a daughter with atomic mass A minus 4, because it's lost 4 particles, and Z minus 2, because it's lost 2 protons, plus the alpha particle, 2 protons, atomic mass of 4, and, as with all these decays, energy. The reason for these decays is that the nucleus of the atom is in an excited state. It's in a state that's not comfortable. It wants to fall down and relax and become more stable. If it's going to fall down and become more stable, then it's going to emit energy. And so these particles that come flying out, in this case a helium nucleus, comes out with lots of energy, typically millions of electron volts, representing the readjustment and settling of the stable daughter nucleus. For beta decay, we can write the same sort of equation. Beta decay occurs for all elements, from the lowest mass to the highest mass, but we'll use some low mass examples. So let's start with boron, number 5 in the periodic table. Boron 12, with 5 protons and 7 neutrons, 5 plus 7 is 12, is actually unstable to beta decay and transforms itself into carbon, 6 protons, 6 neutrons, readily by spitting out an electron. In all of these equations, it's very simple to see what happens. The mass on both sides of the equation must balance, and the charge on both sides of the equation must balance. 5 positive charges on the left of the equation with boron becomes 6 positive charges in the carbon atom minus 1 negative charge from the electron that's ejected equals 5. 6 minus 1 equals 5. And the 12 atomic mass units of boron, the number of protons plus neutrons, 7 plus 5, is equal to 12, the number of protons plus neutrons in carbon, although now it's 6 of each. The electron doesn't count for having atomic mass because it's not one of those particles composed of quarks. However, the electron is a lepton, you remember, the other family of fundamental particles, and you can't just create leptons out of nothing either. You have to have a balancing particle. And the balancing particle in this case is the anti-neutrino. So, balancing charge and mass and the number of leptons on both sides of the equation, we have 5 equals 6 minus 1, 12 equals 12 plus 0, and 0 leptons on the left equals 0 leptons on the right because the electron has an electron number of 1. And the anti-neutrino, being anti, has an electron number of minus 1. Thus, in general, for beta decay, we have a parent nucleus of atomic mass A and atomic number Z becoming a daughter nucleus of still atomic mass A, same number of protons plus neutrons, but one more proton, Z plus 1, it's taking one step up in the periodic table, plus the electron and the antineutrino. Again, both the electron and the antineutrino carrying away significant amounts of energy. Beta decay, as I said, has several forms. That's the simplest one. The other kind is inverse beta decay, or decay, rather than spitting out a negative electron, spitting out its antiparticle, a positive electron. Again, we'll take a light element example. Nitrogen is number 7 in the periodic table and thus has 7 protons. Nitrogen 12 has only 5 neutrons, and that's not quite enough to stabilize its nucleus. It's not enough extra glue from the neutrons to overcome the repulsive force of the protons inside that nucleus. And so it wants to readjust. And it readjusts also to become carbon 12, 6 protons and 6 neutrons, which means it has to get rid of a positive charge. 7 equals 6 plus 1, the positive charge coming out in the form of the positron, the anti-electron. And again, because we must also balance the number of leptons on the two sides of the equation, there are none on the left, so there must be a net total of none on the right. The positron antiparticle comes out accompanied by a normal kind of neutrino, again, both carrying away energy. So inverse beta decay effectively is taking a proton and transforming it into a neutron plus a positron. A neutron which is neutral, and the positron which carries away the plus charge that the proton used to have. So in general, the parent of atomic mass A and number Z becomes the daughter of atomic mass A and number Z minus 1, plus the positron plus the neutrino. Electron capture is the third sort of beta decay process that can occur. We use the example here from beryllium. Beryllium is number 4 in the periodic table, and if it only has 3 neutrons, it's got too few neutrons for the number of protons. What it can do, if an unwary electron on its inner orbit happens to wander too close to the nucleus, it can gobble it up, sucking in the negative charge to the nucleus, therefore reducing the number of protons by 1 and becoming the element lithium, number 3. Again, we see that 4 minus 1 equals 3 plus 0, and 7 plus 0 equals 7 plus 0. We have one lepton on the left side of the equation, so we must have one on the right side, an electron and a neutrino. Effectively, in this case, what's happening is a proton plus an electron are coming together, plus and minus charge, to make a neutron. We're transforming a proton into a neutron. So again, in general, the parent of atomic mass A and number Z plus an electron becomes the daughter of atomic mass A and number Z minus 1 plus the neutrino, and as always, with energy. Finally, there's gamma decay, in which an excited nucleus, which we represent as the symbol for the element with a little asterisk next to it, indicating it's excited, is going to simply get rid of energy in the form of electromagnetic radiation, high-energy gamma rays. So thallium, which in the alpha decay was produced from bismuth, might be produced in an excited state. And so it becomes thallium, again, with the same number of protons, same number of neutrons, no change at all, but emits a gamma ray. A photon has no charge and no mass, and so its quantities are 0 and 0. In gamma decay, the excited parent becomes the same parent with the same atomic mass and the same atomic number, but with less energy because it's become unexcited. The nucleus, as I said several lectures ago, is analogous to the electron structure around the atom. It has various levels in which its particles can exist and be happy. We see here that bismuth 212 has an energy that's 6.1 million electron volts greater than the energy of a relaxed
thallium
nucleus. However, when the bismuth spits out its alpha particle, it leaves a jumbled mess inside, and rarely does it fall immediately to the lowest energy state
of thallium.
Several states indicated for hundredths of a million electron volt above 0, 33 hundredths, 47 hundredths, and 49 hundredths. The bismuth decay can result in the thallium atom ending up in any of those different states. If it falls immediately to the most relaxed state, the alpha particle carries away the full 6.1 million electron volts. If, on the other hand, which is more likely, it falls into one of the excited states, the alpha particle will carry away the 5.61 million electron volts of energy that represents the difference between the bismuth state and the
upper level of thallium.
And then
the thallium nucleus,
finding itself excited, will relax and fall down to the state of 0 MeV, meaning a photon, a gamma ray, of 0.49 MeV is given off. Any of the other intermediate states are also possible. So the key to radioactive instability is the ratio of protons to neutrons in a nucleus. Neutrons add a strong force glue to help overcome the electrical repulsion of all those positively charged protons that are in the nucleus. Each element has an optimal ratio of protons to neutrons, which yields the most stable arrangement, and in some cases, many arrangements are stable over long periods of time. The first 82 elements in the periodic table have from 1 to 10 different stable isotopes, which, as far as we know, will live effectively forever. The last 10 elements in the periodic tables, numbers 83 through 92, actually have no stable isotopes. All of their possible arrangements of protons and neutrons eventually fall apart, although some of them live a very long time, for billions and billions of years before doing so. Radioactive decay always is designed to propel the nucleus towards a more stable arrangement of the protons and neutrons, pushing them towards the proton-neutron stability curve. We can show this conveniently in a graph, where we plot on the y-axis the number of neutrons, and on the x-axis the number of protons. Now, in any such graph, where we plot one set of numbers versus another, the line at 45 degrees represents equality. Same number of protons and same number of neutrons. For the low atomic number particles, for the ones in the beginning of the periodic table, equality equals stability. Helium has 2 protons and 2 neutrons. Carbon has 6 protons and 6 neutrons. Nitrogen has 7 of each. Oxygen has 8 of each. Stability equals equality. But as we go up the periodic table, to pack more and more positive charges into the nucleus, we need extra glue. We need extra neutrons in there to help make the nucleus stable. And so the line of stability starts to depart from the line of equality, rising steadily above it until we get to the element uranium, which has 92 protons but 146 neutrons. In all cases, radioactive decay is designed to take an isotope that lies away from this line of stability, or to be fair, really a valley of stability because the line is not infinitely narrow, towards that line. Alpha decay, for example, occurs in heavy elements which up here will lose 2 protons and 2 neutrons, so therefore move on a 45-degree line, where the valley of stability is more steep. So it moves towards the valley of stability. Beta decay loses a neutron and gains a proton. So it moves down and to the right, and any isotope that's above the line of stability will therefore move towards it. Inverse beta decay occurs in elements that are below the line, because if you lose a proton this way and gain a neutron this way, you move up and to the left, and as a consequence, you again approach the line. Radioactive decay is fundamentally a probabilistic process. Nothing in the environment can affect the decay of an unstable nucleus. This is very unlike all the other properties of things we know. In chemistry, you can drastically affect the rate at which a chemical reaction occurs, or even whether the chemical reaction will or won't occur if you change the environment. If you add a magnetic field, if you surround it with other atoms, if you change the temperature, if you change the chemical composition of the surrounding medium, all these things affect the way chemical processes go. Not so for nuclear processes. There is no way you can alter radioactive decay. This is tremendously advantageous if we want to use these radioactive nuclei as imperturbable clocks. However, there's an inconvenience that comes along with this, and that is you can never predict when a given radioactive decay will occur. It's very much like flipping a coin. So, for example, if you have a radioactive nucleus sitting on your desk and you think it's going to decay, head says it decays, tail says it's not, it's tails. It doesn't decay. You can then flip again after waiting a little while, and lo and behold, it's tails again. So it still doesn't decay. And you can flip it a third time, and finally, aha, it's heads, and the atom decays. Just because I got two tails the first time, however, does not mean that it was more likely that I get heads the next time. This is called the gambler's fallacy. It's if you get 5 heads in a row, if you get 15 heads in a row, it is still not more likely that the next flip will be tails. Every flip is independent. And there is exactly a 50-50 chance that after 15 heads in a row, you will flip a tails. Likewise, for a radioactive nucleus, it can sit there for a very long time before it decays, and then suddenly it will do so, unaffected by the outside world and unpredictable from physics that we know. This is one of the aspects of physics on the subatomic scale which disturbed Einstein greatly. His famous quote on this subject was that God does not throw dice. He could not believe that there wasn't some underlying mechanism which would, if we understood it, allow us to predict when a particular nucleus would decay. That was 80 years ago. We still haven't found it. As far as we can tell, nature is fundamentally probabilistic at this very low level. However, that doesn't mean that we can't say anything about when this particular radioactive nucleus will decay. In fact, every single radioactive isotope has a very precisely defined quantity termed its half-life, which tells us, equivalently, either 1, what the odds are that this particular nucleus will decay when it has a 50-50 chance of having decayed, or alternatively, and perhaps easy to picture, if we have a large quantity of these radioactive nuclei, all the same, when 50% of them will have decayed. The half-life should be thought of as when half of the substance in question has decayed. Now, nuclei individually have no memories, so they don't know when you start counting the half-life. Thus, radioactive decay has a characteristic curve called an exponential, which behaves as follows. Let's say I start with 1,000 nuclei, and the half-life is 1 minute. After 1 minute, the odds are I'll have 500 left. It may be 503, it may be 493, but I'll have roughly 500 left. But those 500 nuclei won't all disappear in the next half-life because they don't know when I started counting. Those 500 nuclei always think they have a 50% chance of decaying in 1 minute. So, after the next minute, after 2 minutes, there won't be 0 left, there'll be 250 left. Half of the 500 at the beginning of the second minute. And after the third minute, there'll be 125 left. That is, I go from the 100% of the substance to 50%, to 25%, to 12.5%, to 6.25%, steadily downward, getting ever closer to 0, but if I have a very large number of particles, not reaching it for a very long time. The number of particles left at any given moment is equal to the number you start with times 1/2 raised to the power the time which you've gone by divided by this half-life. And the half-life is unique for every different isotope. Half-lives range from a tiny fraction of a second for atoms that we rarely see to tens of billions of years, longer than the age of the universe for some of the heavy isotopes. Now, as a consequence of the unique and immutable half-lives, radioactive isotopes can be used as clocks. In some cases, for example, radioactive parent nuclei produce stable daughter nuclei. This is often, but not always, the case. Therefore, suppose I have a rock that got melted in the interior of the Earth and shot out of a volcano at some time in the distant past. This rock contains lots of different kinds of atoms in the mix of minerals that make it up. And in particular, it's likely to contain radioactive nuclei. If those radioactive nuclei trapped in the crystalline structure of the rock now undergo decay, producing either alpha particles or electrons or positrons or gamma rays, the decay product is stuck there in the rock. It might be the wrong kind of element to fit in that place in the crystal lattice of the rock because the rock was formed with this other kind of element, 2 or 1 removed in the periodic table. But the daughter is stuck there. As time goes by, these radioactive nuclei continue to decay. And so much time may go by, millions, tens of millions, hundreds of millions of years, until there are no parent nuclei left anymore. But the daughters are still all trapped. If I come across this rock as a geologist and now want to determine how old it is, that is, when it was last in a magma state and thrown out of a volcano, all I have to do is go in and count the number of daughter nuclei. Those daughter nuclei may, for example, be a noble gas, a gas that doesn't interact chemically in any way and therefore doesn't belong in a crystal at all. But if I smash the rock and I boil out this noble gas and count the number of atoms, I can say how many of the parent nuclei there were, and if there are still any parent nuclei left, by taking the ratio of the number of daughters to the number of parents left, I can measure the age of the rock. Some daughter nuclei only arise from a specific kind of parent. So even if the parent is all gone, I can count up the number of daughter nuclei and know the original abundance of the parent. This, it turns out, is critically important in determining the age of the Earth and the meteorites which formed the solar system. For things that were once alive, the radioactive isotope of carbon, carbon-14, with 6 protons and 8 neutrons, is an invaluable dating tool. Carbon-14, somewhat unusually, has a half-life really appropriate for human history. It's 5,730 years. So after 5,730 years, half of a sample of carbon-14 will have decayed into nitrogen-14, a stable nucleus. Carbon-14, if it was only produced in the beginning of the universe or in the stars that created the material out of which the sun was born 4.5 billion years ago, would be all gone because its half-life is 5,000 years, and after 5 billion years, there'd be none left at all. However, carbon-14 is constantly being produced in the atmosphere by cosmic rays which strike nitrogen atoms and turn them spontaneously into carbon-14. Cosmic rays are these extremely high-energy particles that are produced in the remnants of exploded stars. Such stars will be visited by us in this lecture series. And they contain so much energy that they shatter any nucleus they come to. They can travel clear across the galaxy. An individual proton or neutron can have the energy of a tennis ball hit at 120 miles an hour. And remember how small those particles are. They smash into the atmosphere, knocking apart atoms willy-nilly, and create carbon-14. Now, carbon-14 is absorbed into plants just like the more common and stable form carbon-12. And when the plant dies, no more carbon is being incorporated. The carbon-12 remains stable, but the carbon-14 starts to decay. And as it decays away, we can use the ratio of carbon-12 to carbon-14 as an accurate dating method for any sample that was originally alive. We can use this back for 60,000 years. We will see several examples of this throughout the course. Carbon-14 is the only common isotope that has a half-life that's that relevant to human history. But as we shall see, we can use other stable and unstable isotopes in our reconstruction of the history of everything else, from small paintings to the entire universe.